Every time you flip a switch, send a message, or look up at the stars, light is already racing ahead of you, and yet it never goes any faster than it already does. No matter how powerful the engine, how violent the explosion, or how advanced the technology, the universe enforces a hard limit, a cosmic speed barrier that nothing has ever broken. Scientists did not just assume this limit exists, they ran straight into it while trying to understand space, time, and reality itself, and what they found was unsettling. The speed of light is not just about light, it is about how fast cause and effect can happen, how the universe keeps events in order, and why time itself behaves so strangely near extreme speeds. Push anything closer to this limit, and space begins to compress, time begins to slow, and energy demands spiral toward infinity. This is not a technical inconvenience, it is a deep rule woven into the structure of the universe. Leave a like and subscribe to the channel as tonight we look into the mysteries behind the speed of light. Get ready, we begin. Let me begin with something that may catch you off guard. Light's velocity was among humanity's earliest precise cosmic measurements. Throughout most of human history, people believed light moved instantly. Opening your eyes meant seeing everything right away, didn't it? It felt natural to think light required no travel time whatsoever. However, in 1676, a scientist from Denmark named Ole Romer observed something unusual. During his study of Jupiter's satellites, he noticed the moons appeared to arrive early when Earth moved nearer to Jupiter and late when Earth travelled farther from it. The sole reasonable explanation was that light needed time to span the additional space. Based on these observations, Romer determined that light moved at a limited velocity. His calculation came to roughly 140,000 miles per second, impressively near the actual number given the primitive equipment of his era. This finding was groundbreaking, yet it marked just the start. Over the following centuries, researchers improved their light speed calculations through increasingly ingenious approaches. By the late 19th century, scientists like Albert Michelson had determined light's velocity with remarkable accuracy. But these accurate calculations created a mystery that would rock physics to its core. Here's where matters become strange. Based on everything researchers understood about movement, velocity should combine in a simple manner. If you're riding a train going 60 miles hourly and toss a ball ahead at 20 miles hourly, somebody standing on the platform should observe the ball travelling at 80 miles hourly. This seems like basic reasoning, correct? Yet light refuses to obey this principle. The Michelson-Morley test in 1887 attempted to find variations in light's velocity as Earth travelled through the cosmos. Earth circles the Sun at roughly 67,000 miles hourly, so light travelling in the matching direction should look quicker than light travelling the reverse direction. But that wasn't their discovery. Regardless of which direction they measured, no matter what season, light invariably moved at precisely the identical velocity. This outcome was so stunning that numerous scientists wouldn't accept it. They created complex theories about invisible materials called ether that supposedly transported light waves. Yet every effort to preserve the previous understanding didn't work. Light's velocity was unchanging, full stop. It wasn't affected by your movement, Earth's movement, or anything else whatsoever. Then came Albert Einstein, a 26-year-old patent office worker with a radical concept. In 1905, Einstein released his special relativity theory, which began with two basic assumptions. Physics laws remain identical for all watches travelling at steady velocities, and light's velocity in empty space stays identical for all watches, independent of their movement. From these two ideas, Einstein worked out results that appear to challenge basic reasoning. Time moves slower for things traveling at great velocities. Distances shrink in the travel direction. Mass and energy are the same thing, connected by the celebrated formula E equals mc squared. And crucially for our discussion, nothing possessing mass can ever achieve light's velocity. To grasp why, you need to understand something basic about what occurs as you near light speed. Imagine you're in a spaceship with an enormously strong motor. As you speed up, something odd occurs. The quicker you travel, the more energy it requires to boost your velocity even slightly more. At regular speeds, this influence is tiny. Doubling your velocity roughly doubles the required energy. But as you get close to light speed, the energy needs skyrocket toward infinity. At 50% of light velocity, you'd require about 15% extra energy than Newton's principles would forecast. At 90% of light velocity, you'd need over twice as much. At 99%, you'd require 7 times more. At 99.9%, you'd need 22 times more. The pattern is obvious and unforgiving. The nearer you get to light speed, the more energy you require for every extra mile hourly. To genuinely reach light velocity, you would require endless energy. Not merely lots of energy, but literally boundless energy. Since the cosmos holds only a limited quantity of energy, achieving light speed proves impossible for anything possessing mass. But why does this occur? The explanation lies in the character of space and time themselves. Einstein demonstrated that space and time aren't distinct, unchanging platforms where happenings occur. Rather, they're features of a 4-dimensional structure called space-time. When you travel through space, you're simultaneously traveling through time, and your combined velocity through space-time always matches light's velocity. Consider it this way. When you're sitting motionless, all your movement is through time. You're journeying into tomorrow at 1 second per second. But when you begin traveling through space, some of that movement gets redirected. The quicker you travel through space, the more slowly you travel through time. This explains why time dilation happens. It's not a malfunction or trick, but a basic characteristic of how space-time operates. This universal speed restriction isn't random. It's embedded in space-time's geometry itself. Asking why nothing can travel quicker than light resembles asking why you cannot sketch a square circle. It's not a regulation imposed externally. It's part of what space and time actually mean. The proof for this universal speed restriction comes from innumerable tests and observations. Particle accelerators, like the Large Hadron Collider, regularly speed up protons to 99.9999% of light velocity. Despite using energies that could run a modest city, they cannot push particles that last a small portion to achieve light speed. The particles acquire energy, but rather than traveling quicker, they grow more massive, precisely as Einstein forecasted. GPS satellites offer daily confirmation of these influences. These satellites circle Earth at great velocities and feel reduced gravity compared to us on the ground. Both influences make their clocks run at varying rates than Earth clocks. Without adjustments for these relativistic influences, GPS would gather mistakes of roughly 6 miles daily. The reality that GPS operates is confirmation that Einstein's speed restriction is genuine and impacts your everyday existence. Cosmic ray particles supply even more striking proof. These high-energy particles formed in fierce cosmic happenings crash into Earth's air at velocities incredibly near light speed. Some possess energies millions of times larger than anything we can generate in laboratories. Yet even with these huge energies, they never surpass light speed. The cosmos's strongest particle accelerators, bursting stars, crashing galaxies, feeding black holes, all honor the universal speed restriction. But here's where matters become even more intriguing. Light's velocity isn't truly about light whatsoever. It's the velocity of causality, the highest rate at which cause and effect can spread through space. Light happens to travel at this velocity because photons possess no mass. But the deeper reality is that information itself cannot move quicker than this universal restriction. This link between light's velocity and causality produces one of the most brain-twisting consequences of Einstein's theory. If you could somehow move quicker than light, you wouldn't merely be violating a speed restriction, you'd be journeying backward in time. This isn't fantasy, it's a straightforward mathematical result of how space-time operates. To grasp why, picture you have a companion on a far-off planet 4 light-years distant. If you could transmit a message quicker than light, say in merely 1 year, here's where matters get strange. From the viewpoint of somebody traveling at great velocity compared to you and your companion, your instant message would reach before it was transmitted. They would observe effect coming before cause, which would permit paradoxes like transmitting a message to your earlier self, instructing you not to transmit the message initially. The cosmos appears to possess built-in safeguarding against such paradoxes. The velocity of light forms what scientists call a light cone, a limit in space-time that divides happenings that can causally affect each other from those that cannot. Your upcoming light cone holds all the happenings you could potentially affect. Your earlier light cone holds all the happenings that could have affected you. Happenings beyond these cones are in what's termed elsewhere, areas of space-time that cannot interact with you without surpassing light speed. This arrangement of space-time, with its embedded speed restriction, isn't a flaw. It's a characteristic. It guarantees that cause invariably comes before effect, that the cosmos maintains reasonable consistency, and that reality develops in an organized manner. Without this universal speed restriction, the cosmos would be a disorderly mess where effects could come before causes, and the very idea of before and after would collapse. But hold on, you might be wondering, haven't you heard about things that do move quicker than light? What about quantum entanglement, where particles appear to affect each other immediately across enormous distances? Or space's expansion itself, which can transport galaxies apart quicker than light? These are superb questions that expose the delicate character of the universal speed restriction. Let's address quantum entanglement first. When two particles are entangled, measuring one does immediately impact the other, regardless of how distant they are. Einstein labeled this spooky action at a distance and was greatly bothered by it. Contemporary tests have verified that this connection is genuine and does occur quicker than light could move between the particles. But here's the vital point. While the connection is immediate, you cannot utilize it to transmit information quicker than light. The outcomes of measurements on entangled particles are unpredictable. Only when you compare the outcomes, which needs regular, slower than light communication, do you observe the connection. Quantum entanglement resembles having two coins that invariably land on reverse sides, regardless of how distant they are when flipped. The connection is genuine, but you cannot utilize it to transmit a message. Regarding space's expansion, this is truly occurring quicker than light for adequately far galaxies. But this doesn't break the universal speed restriction because the galaxies aren't traveling through space quicker than light. Space itself is growing between them. It resembles dots on an expanding balloon separating without genuinely traveling across the balloon's surface. The speed restriction applies to movement through space, not to space's expansion itself. Speaking of universal mysteries, if you're captivated by how space itself can grow, you'll be astounded by what might exist past the edges of our visible cosmos. In my video titled, "What Lies Beyond the Edge of the Universe?", I investigate brain-twisting possibilities from boundless cosmic expanses to parallel universes and additional dimensions. Look at the link in the description to continue your exploration into the biggest cosmic questions. Now, returning to our investigation of the universal speed restriction, these subtleties emphasize something deep. The cosmos's speed restriction is more advanced than a basic regulation stating nothing travels fast. It's a basic principle about information's character, causality, and space-time's arrangement itself. Now let's investigate what genuinely occurs when you push against this universal speed restriction. The influences are stranger than fantasy, yet they're verified by innumerable tests and observations. Grasping these influences will show you why light's velocity isn't merely a barrier to overcome, but a basic characteristic that molds reality itself. Time dilation is likely the most celebrated influence. As you get close to light velocity, time literally moves slower for you compared to the remaining cosmos. This isn't a trick or a measurement mistake. Time itself flows at varying rates for things traveling at varying velocities. The mathematics is beautifully straightforward. At half-light velocity, time passes about 87% as quickly as regular. At 90% light velocity, time passes at 44% regular rate. At 99%, it's reduced to 14%. At 99.9%, time creeps by at merely 4.5% its regular rate. This has been verified by innumerable tests. In 1971, scientists Haefel and Keating transported atomic clocks around the planet on regular airplanes. When contrasted to comparison clocks on the surface, the travelling clocks had aged somewhat less by precisely the quantity Einstein's formulas forecasted. The influence was minuscule at airplane velocities, merely nanoseconds, but it was genuine and quantifiable. Particle accelerators supply more striking verification. Unstable particles termed muons are formed when cosmic rays strike Earth's air. These muons possess a quite brief lifespan, about 2.2 microseconds. At that rate, even moving at near light velocity, they should break down before arriving at Earth's surface. But we find them at ground level constantly. Why? Because at their great velocities, time dilation extends their lifespan from our viewpoint, providing them time to finish the trip. From the muon's viewpoint, something similarly odd occurs. To the muon, its lifespan remains 2.2 microseconds. But the space to Earth's surface has shrunk due to length contraction, another relativistic influence. The muon observes a much briefer trip, which it can finish in its short lifespan. Both viewpoints are similarly correct and produce the identical outcome. The muon arrives at Earth's surface. This length contraction is equally genuine as time dilation. As you get close to light velocity, spaces in your travel direction literally reduce. At 90% light velocity, spaces shrink to 44% of their starting length. At 99.9%, they reduce to merely 4.5%. Picture you're journeying to Proxima Centauri, the closest star to our Sun, about 4.2 light-years distant. At 99.9% light velocity, the trip would require about 4.2 years from Earth's viewpoint. But from your viewpoint inside the spaceship, the space would shrink to merely 0.2 light-years, and the trip would require only 2.4 months. You would age 2.4 months, while Earth aged 4.2 years. This isn't a trick or trick. Both time measurements are genuine. There's no right reference frame. This is relativity's deep insight. Space and time aren't absolute but rely on your movement. The cosmos doesn't possess a master clock or a favoured ruler. Every watcher's measurements are similarly correct. These influences produce the celebrated twin paradox. Picture identical twins, where one remains on Earth while the other journeys to a far star at near-light velocity. When the journeying twin comes back, they'll have aged much less than their Earthbound sibling. If the trip involved velocities of 99.9% light velocity to a star 20 light-years distant, the journeying twin would age about 1.8 years, while the Earth twin aged 40 years. This isn't theoretical. It occurs every day in particle accelerators and with cosmic rays. We've watched particles existing far longer than they should because of time dilation. In a quite genuine sense, getting close to light velocity is a type of time journey to tomorrow. The quicker you travel, the more you can leap ahead in time compared to the remaining cosmos. But there's a cost for this temporal shortcut: mass-energy similarity. As you get close to light speed, your relativistic mass grows. This doesn't mean you're acquiring atoms or getting larger. Rather, the energy of your movement shows up as boosted resistance to additional acceleration, what scientists term inertial mass. At regular speeds, movement energy obeys the recognizable formula from high school science: 1/2 mass times velocity squared. But at great velocities, the genuine formula involves the Lorentz factor, which gets close to infinity as you get close to light velocity. This explains why particle accelerators require exponentially more energy to push particles slightly nearer to light velocity. The Large Hadron Collider offers a flawless example. It speeds up protons to 99.99999% light velocity. At this velocity, each proton possesses about 7,000 times its resting mass worth of movement energy. The LHC uses adequate electricity to run a modest city, yet it can only push particles to within a minuscule portion of light velocity, never achieving it. This takes us to one of the most deep insights about the universal speed restriction. Mass and energy are basically the identical thing, connected by Einstein's celebrated formula: E equals mc squared. The c in this formula isn't merely light's velocity, it's the conversion element between mass and energy, the basic constant that connects space to time. When you warm up a cup of coffee, it genuinely becomes somewhat more massive due to the added heat energy. When the sun combines hydrogen into helium, the mass variation changes to energy based on E equals mc squared. Every chemical reaction, every biological process, every thought in your brain involves minuscule changes between mass and energy, controlled by this universal constant. This explains why light's velocity is so distinctive. It's not merely a speed restriction, it's the basic constant that establishes the connection between space and time, between mass and energy, between cause and effect. It's interwoven into reality's structure at the deepest level. But what about those fantasy stories about warp engines and wormholes? Don't they provide methods around the universal speed restriction? The astonishing answer is that some of these ideas are theoretically feasible within Einstein's formulas, but they arrive with catches that make them practically impossible or paradoxical. Let's begin with wormholes. In 1935, Einstein and his associate Nathan Rosen found that general relativity's formulas permit bridges linking far areas of space-time. These Einstein-Rosen bridges, or wormholes, could theoretically permit journey between far parts of the cosmos without surpassing light velocity locally. The crucial word here is locally. A wormhole doesn't allow you to move quicker than light. It offers a shortcut through space-time. Picture an ant walking on a piece of paper. If the paper is level, the ant must walk the complete space between 2 points. But if you fold the paper so the 2 points touch, the ant can step across immediately. The ant never surpasses its highest walking velocity. It merely takes advantage of the paper's shape. But here's the problem. Wormholes that could genuinely be crossed would need exotic material with negative energy density, something that has never been watched and might not exist. Even if crossable wormholes could exist, they would probably be enormously unstable. The instant anything attempted to pass through, they would fall apart quicker than light could cross them. Stephen Hawking suggested the chronology protection hypothesis, the concept that physics laws, somehow stop the formation of time machines. Every theoretical approach of faster-than-light journey or time journey appears to possess a built-in flaw that makes it impossible. It's as if the cosmos possesses a security system against paradoxes. The Alcubierre warp engine, suggested by scientist Miguel Alcubierre in 1994, provides another theoretical loophole. This idea involves shrinking space ahead of a spaceship and growing it behind, forming a warp bubble that transports the ship quicker than light compared to far watchers. The ship itself never surpasses light speed within its local bubble of space. But again, there are devastating difficulties. The Alcubierre engine would need huge quantities of exotic material, by some calculations, more than the mass energy of the entire visible cosmos. It would additionally form causality paradoxes, permitting time journey into the earlier past. And recent investigation suggests that even if you could form such an engine, you couldn't manage it. You'd be causally separated from the front of the warp bubble. These theoretical possibilities instruct us something significant. The cosmos's speed restriction is more delicate and more basic than a straightforward prohibition. It's not that the cosmos possesses a regulation against traveling fast. Rather, space-time's arrangement itself makes faster-than-light journey logically incompatible with causality. Let's discuss tachyons, hypothetical particles that invariably move quicker than light. Relativity's mathematics doesn't genuinely prohibit such particles from existing. Actually, the formulas work flawlessly well for particles that invariably move quicker than light, just as they do for particles that invariably move slower than light. But tachyons would possess strange properties. They would possess imaginary mass in the mathematical sense of involving the square root of -1. They would speed up when they lose energy and slow down when they acquire energy. Most problematically, they could be utilized to transmit signals into the earlier past, forming causality paradoxes. Despite decades of looking, no test has ever found a tachyon. Most scientists think they don't exist, and that their lack is another instance of the cosmos's safeguarding against paradoxes. The universe appears to be built in a manner that maintains the reasonable flow of cause and effect. This takes us to a deep question. Why does the cosmos possess this specific speed restriction? Why 186,282 miles per second and not some other number? The explanation touches on reality's basic character itself. Light's velocity is connected to two other basic constants, the permittivity and permeability of empty space. These constants establish how electric and magnetic fields act in emptiness. Maxwell's formulas, which explain electromagnetism, demonstrate that electromagnetic waves, including light, must move at a velocity established by these constants. But this merely pushes the question back a level. Why do space's permittivity and permeability possess the numbers they do? This is part of a bigger mystery in science. Why do nature's basic constants possess the particular numbers we watch? Some scientists invoke the anthropic idea, the concept that we watch these specific numbers because they're compatible with our existence. If light's velocity was considerably different, the cosmos might not be capable to form stars, planets, or life. We discover ourselves in a cosmos with this specific speed restriction because universes with varying numbers wouldn't possess watchers to measure them. Others guess about a multiverse where varying areas possess varying basic constants, including varying speed restrictions. We would naturally discover ourselves in an area where the constants permit complex arrangements and life. But these concepts remain greatly speculative and may be untestable. What we do understand is that light's velocity is closely linked to space-time's arrangement itself. In Einstein's theory, space and time are combined into space-time, and light's velocity is the conversion element between space and time. Asking why light moves at this specific velocity resembles asking why there are 3 feet in a yard. It's a basic part of how we measure the cosmos. The universal speed restriction additionally plays a vital role in quantum field theory, our most successful structure for grasping particles and forces. In this theory, particles are disturbances in quantum fields that fill all of space. Light's velocity establishes how these field disturbances spread, setting the highest rate at which particles can affect each other. Virtual particles, temporary changes in quantum fields, can appear to break the speed restriction, but only within the uncertainty principle's limits. The more they surpass light velocity, the briefer their existence must be. The cosmos permits these short violations as long as they average out to honor the universal speed restriction. This quantum viewpoint exposes another aspect of why nothing can surpass light speed. Doing so would break reality's basic quantum arrangement. Faster-than-light particles would form inconsistencies in quantum field theory, producing nonsensical forecasts like negative probabilities. Light's velocity additionally establishes the power of electromagnetic interactions. If light moved quicker, electric and magnetic forces would be less strong. If it moved slower, they would be more powerful. The specific number we watch permits the rich chemistry that makes life feasible. Atoms can form stable connections, molecules can possess complex arrangements, and information can be stored and handled in biological systems. Speaking of information, the universal speed restriction applies not merely to material and energy, but to information itself. No signal, no message, no effect of any sort can spread quicker than light. This restriction molds everything from computer design to the hunt for alien intelligence. When you transmit a text message to somebody on the opposite side of Earth, it moves through electromagnetic signals that travel at light velocity. The delay is minuscule, about 67 milliseconds to travel halfway around the planet, but it's there. For communication with spacecraft investigating the solar system, the delays grow noticeable. A signal to Mars requires between 4 and 24 minutes depending on the planet's positions. For interstellar spaces, the restriction becomes deep. A conversation with somebody on Proxima Centauri would involve a minimum 8.4-year round-trip delay. This universal speed restriction doesn't merely make interstellar journey difficult, it makes interstellar civilization as we picture it nearly impossible. Any galactic empire would be restricted by light's velocity, requiring years or centuries for messages to cross between star systems. But here's a beautiful thought. The identical speed restriction that separates us additionally links us. When you gaze at the night sky, you're observing the cosmos's history written in light. That star you're gazing at might be 10 light-years distant, meaning you're observing it as it was 10 years earlier. That galaxy might be 1,000,000 light-years far, showing you a 1,000,000-year-old picture. By the way, if you are appreciating the video, please think about giving a thumbs up and subscribing. I am beginning now on YouTube, and your assistance really means a lot to me. Let's proceed. The universal speed restriction transforms the cosmos into a huge time machine. The more distant you gaze, the more backward in time you observe. The most far galaxies visible to our telescopes show us the cosmos as it was over 13 billion years earlier, when the first galaxies were forming. We can literally observe cosmic development happening by gazing at things at varying spaces. This cosmic time machine influence has deep consequences for astronomy and cosmology. When the James Webb Space Telescope captures pictures of the most far galaxies, it's not merely observing distant, it's observing distant back in time. Those ancient galaxies appear as they were when the cosmos was young, permitting us to straightforwardly watch how galaxies formed and developed. The limited velocity of light additionally means that the visible cosmos possesses a limit, not in space but in time. We can only observe things whose light has possessed time to arrive at us since the Big Bang, 13.8 billion years earlier. Past this universal horizon lies the unobservable cosmos, forever concealed from our view, not by space, but by the cosmos's limited age and the universal speed restriction. This restriction might appear frustrating, but it's additionally protective. If light moved endlessly fast, the night sky would be endlessly bright. Every sight line would eventually strike a star, and their combined light would burn everything. The limited velocity of light, combined with the cosmos's growth and limited age, provides us the dark night sky that permits life to exist. Light's velocity additionally molds how we grasp gravity. In Newton's theory, gravity operated immediately across any space. If the sun suddenly disappeared, Earth would immediately fly off in a straight line. But this instant action at a distance bothered scientists, including Newton himself. Einstein's general relativity solved this mystery by demonstrating that gravity isn't a force but space-time's bending. Changes in this bending spread at light velocity. If the sun disappeared, Earth would proceed circling for about 8 minutes, the time it requires light to move from the sun to Earth. Only then would Earth sense the gravitational change and fly off into space. This forecast was spectacularly verified in 2017 when the LIGO and Virgo detectors watched gravitational waves from crashing neutron stars. Telescopes additionally observed the light from this crash. Despite moving 130 million light-years, the gravitational waves and light reached within seconds of each other, verifying that gravity and light move at the identical universal speed restriction. Speaking of universal mysteries, if you're captivated by what might exist past our cosmos, you'll be astounded by what might have existed right here on Earth before humans. Could an advanced civilization have flourished millions of years earlier? I investigate this brain-twisting NASA theory in my video, What If We Are Not the First Civilization on Earth? Link in the description. Now returning to our exploration through the universal speed restriction. The universality of this speed restriction exposes something deep about space and time's character. They're not merely a passive background for happenings, they're dynamic, interconnected features of a combined space-time. The universal speed restriction is the thread that interlaces space and time together into reality's structure. This interconnection appears in astonishing places. Take the straightforward act of moving your hand. When you choose to move, the signal moves from your brain down your nerves as an electrical pulse. These nerve signals move much slower than light, about 200 miles hourly. But they still obey the universal speed restriction. The electrical fields that transport the signal spread at light velocity, even though the signal itself travels much slower due to neurons' biology. Even your thoughts are limited by the universal speed restriction. The electrical and chemical signals in your brain cannot surpass light velocity. This might appear like a minor restriction, but some researchers guess it places basic limits on consciousness and intelligence. Regardless of how advanced a brain or computer might be, its handling velocity is ultimately restricted by how quickly signals can move between its parts. This takes us to an intriguing question about artificial intelligence and advanced civilizations. Could an advanced AI or alien intelligence discover methods around the universal speed restriction? The answer appears to be no. Any information handling system, whether biological or artificial, must obey the identical basic physics laws. Actually, light's velocity places firm restrictions on computation. There's a highest rate at which any physical system can handle information, known as the Bremerman restriction. This restriction exists because computation needs energy, and light's velocity restricts how rapidly energy can be moved around even a computer the size of Earth. using all available energy optimally couldn't surpass this computational speed restriction. The universal speed restriction additionally molds the cosmos's ultimate fate. As the cosmos grows and speeds up, far galaxies are traveling away from us quicker and quicker. Eventually, they'll be moving back so quickly that their light can never arrive at us. The visible cosmos will reduce, and far galaxies will disappear from view, not because they stop existing, but because space's growth transports them past our universal horizon. In the distant tomorrow, trillions of years from now, our local cluster of galaxies will be alone in an empty, dark cosmos. All other galaxies will have passed past the universal horizon. Tomorrow's civilizations in this era might possess no method to understand about the Big Bang or the cosmos's growth. The proof will have literally disappeared past light's velocity. This cosmic separation highlights another feature of the speed restriction. It doesn't merely limit movement through space, but additionally information's flow and causality. Areas of the cosmos that separate quicker than light grow causally separated. They can no longer affect each other in any manner. It's not merely that communication grows impossible, any type of interaction or effect is cut off. But let's take this back to your everyday existence. How does the universal speed restriction impact you personally, in more manners than you might imagine? Every time you use GPS, you're depending on adjustments for relativistic influences. Every time you undergo a PET scan, you're gaining from our grasp of antimatter, which exists because of the symmetries needed by the universal speed restriction. The electronics in your smartphone depend on quantum mechanics, which is closely linked to light's velocity. Your body's chemistry, atom stability, the sun's energy, all rely on the universal speed restriction's specific number. If it were varying, you wouldn't exist. Even your view of reality is molded by light's limited velocity. When you gaze at your hand, you're observing it as it was a few nanoseconds earlier, the time it required light to move from your hand to your eyes. When you gaze at the moon, you're observing it as it was 1.3 seconds earlier. The sun appears as it was 8 minutes earlier. Everything you notice is somewhat in the earlier past. This delay is usually tiny in everyday existence, but it grows meaningful for contemporary technology. High-frequency traders worry about the milliseconds it requires signals to move between stock markets. Online gamers feel lag due to internet signals' limited velocity. Even conversations on cell phones possess a slight delay as signals bounce off satellites or move through fiber optic cables. The universal speed restriction additionally affects how we consider humanity's tomorrow. If we ever grow into an interstellar species, we'll have to accept that it will require years or decades to journey between stars. There's no warp engine coming to rescue us. Any interstellar civilization will be molded by the universal speed restriction, with colonies divided by years of journey time. Some futurists suggest generation ships, spacecraft where multiple generations exist and die during the trip between stars. Others propose transmitting frozen embryos or digital uploads of human consciousness. But all these suggestions must honor the universal speed restriction. There's no shortcut, no cheat code, no manner around this basic limit. Yet this restriction additionally safeguards us. The identical universal speed restriction that stops us from rapidly arriving at the stars additionally safeguards us from cosmic dangers. Gamma-ray bursts, supernovae, and other cosmic catastrophes cannot impact us quicker than light velocity. We invariably possess warning time equal to our space from the threat divided by light's velocity. The universal speed restriction even molds the hunt for alien intelligence. Any alien signals we find will be old, maybe centuries or millennia old by the time they arrive at us. Any conversation with an alien civilization will involve decades or centuries between messages. The universal speed restriction guarantees that first contact, if it ever occurs, will be a slow, patient process, not the striking encounter often shown in fantasy fiction. This universal speed restriction additionally possesses deep philosophical consequences. It instructs us something basic about reality's character and our place in it. The cosmos isn't merely limited by this restriction, it's established by it. Light's velocity isn't merely a property of light, it's a property of space-time itself, a basic constant that molds everything from particles' behavior to galaxies' development. Let's dive deeper into the quantum realm, where the universal speed restriction takes on even more captivating features. Quantum field theory, our most successful structure for grasping particles and forces, incorporates light's velocity at its core. The uncertainty idea, which states that you cannot simultaneously understand a particle's position and momentum with flawless accuracy, is closely linked to the universal speed restriction. When virtual particles briefly pop into existence from the quantum emptiness, they can temporarily borrow energy as long as they repay it rapidly enough. The more energy they borrow, the quicker they must repay it. This connection is controlled by light's velocity. If particles could surpass light velocity, this delicate quantum accounting would collapse, producing reasonable contradictions and violations of energy conservation. The quantum emptiness itself, the seemingly empty space that fills the cosmos, is constantly bubbling with these virtual particles. Pairs of particles and antiparticles appear and destroy each other within minuscule portions of a second. The velocity at which these changes can spread through space is restricted by the universal speed restriction, forming a sort of quantum foam that provides space its basic arrangement. This quantum foam might be reality's deepest level we can access. At the enormously minuscule Planck length, about 10 to the negative 35 meters, the changes grow so energetic that space and time themselves collapse into a boiling quantum soup. At this scale, the ideas of before and after might lose meaning entirely. The universal speed restriction helps safeguard us from this chaos by smoothing out these changes at bigger scales. Some cutting-edge theories propose that space and time aren't basic, but emerge from deeper quantum processes. In these methods, light's velocity emerges as a collective property of the underlying quantum reality, similar to how temperature emerges from molecules' average motion. The universal speed restriction might be nature's method of keeping causal order in a cosmos built from inherently chaotic quantum foundations. Loop quantum gravity, string theory, and other methods to quantum gravity all must wrestle with the universal speed restriction. Any workable theory of everything must clarify why this specific velocity exists and how it molds the cosmos at all scales. The reality that the identical speed restriction applies to everything from quantum particles to gravitational waves proposes a deep unity in nature's principles. This unity reaches to the four basic forces: gravity, electromagnetism, and the strong and weak nuclear forces. Although these forces look quite different in our regular world, scientists think they were once combined in the extreme conditions of the early cosmos. The universal speed restriction played a vital role in how these forces divided as the cosmos cooled, helping to establish reality's basic arrangement. In the first portions of a second after the Big Bang, the cosmos grew quicker than light in a process termed inflation. This doesn't break the universal speed restriction because, again, it was space itself growing, not things traveling through space. This period of inflation helps clarify why the cosmos looks so uniform on big scales and why it possesses the precise quantity of flatness we watch. Some cosmologists suggest that inflation is eternal, continuously forming new bubble universes in an ever-growing multiverse. Each bubble might possess varying physical principles and varying numbers for basic constants, including light's velocity. In this view, our specific universal speed restriction is merely one possibility among many, and we discover ourselves in a cosmos with this particular number because it permits complex arrangements like stars, planets, and life. This takes us back to the anthropic idea, the concept that we watch the specific physical principles and constants we do because they're compatible with our existence. If a light's velocity was considerably different, atoms might not be stable, chemistry might not operate, or stars might not form. We discover ourselves in a cosmos with this specific speed restriction because universes with varying numbers wouldn't possess watches to measure them. The cosmologist Brandon Carter, who created the term anthropic idea, separated between two versions. The weak anthropic idea, which straightforwardly states that what we watch must be compatible with our existence, and the strong anthropic idea, which proposes the cosmos must permit watchers. The weak version is broadly accepted as reasonable, while the strong version stays controversial among researchers. Whatever the ultimate clarification for the universal speed restriction, its results ripple through every feature of our grasp of reality. It links the biggest scales of the universe to the tiniest quantum changes, offering a combining thread that helps make sense of our complex cosmos. The consistency of this speed restriction across all known phenomena is one of the most impressive validations of contemporary physics. From laboratory tests to astronomical observations, from particle accelerators to gravitational wave detectors, every test verifies that light's velocity is genuinely universal. This consistency provides us confidence that we're revealing something basic about reality, not merely an accidental characteristic of our corner of the universe. The hunt for potential variations in light's velocity continues, however. Some theories propose it might have been varying in the early cosmos, or might vary in enormously strong gravitational fields. The variable speed of light theory, suggested by scientists João Magejo and Andreas Albrecht, proposes that light might have moved quicker in the quite early cosmos, potentially solving some cosmological mysteries. But so far, no convincing proof for variation has been discovered. Observations of far quasars, whose light has been moving for billions of years, display the identical spectral patterns we observe in laboratory tests today, proposing light's velocity hasn't changed considerably over cosmic history. The constancy of light's velocity is so basic to contemporary physics that it's embedded into the quite definition of our measurement units. Since 1983, the meter has been established as the spacelight moves in emptiness in 1/299,792,458th of a second. We no longer establish light's velocity in terms of meters and seconds. We establish the meter in terms of light's velocity and seconds. This redefinition mirrors a deep shift in our grasp. Light's velocity isn't merely another measurement, it's a basic property of space-time that we utilize to calibrate our other measurements. It's more like a conversion element between space and time than a velocity in the regular sense. Philosophers of science note that this makes light's velocity constancy somewhat tautological, true by establishment. But the deeper truth is that the world acts in a manner that makes this establishment useful and consistent with all our observations. The cosmos truly possesses this arrangement, independent of how we select to describe it. This takes us to a captivating question. Is the universal speed restriction identical everywhere in the cosmos? Based on Einstein's theory of general relativity, the local velocity of light is invariably identical, but space-time's bending due to gravity can impact how light moves over big spaces. Near a black hole, for instance, light paths are dramatically bent, forming influences like gravitational lensing. From the viewpoint of a far watcher, light appears to decelerate as it passes through a gravitational field. But locally, At each point along its path, light invariably moves at precisely the identical velocity. The apparent decelerating is due to space-time stretching itself, not a genuine change in light's basic velocity. This constancy in the face of space-time bending is another remarkable characteristic of the universal speed restriction. It's not merely a property of empty space, but a basic feature of reality that stays true even in the most extreme environments the cosmos can generate. Black holes offer a captivating laboratory for investigating the universal speed restriction under extreme conditions. At a black hole's event horizon, space is so severely bent that even light cannot escape. This isn't because light decelerates or halts, it's still moving at full velocity, but because space-time itself is bent in a manner that all paths lead inward. Inside the event horizon, space and time effectively switch roles. Just as you cannot help traveling forward in time in the regular world, inside a black hole, you cannot help traveling toward the center. The universal speed restriction still applies, but space-time's arrangement is so distorted that even traveling at light velocity isn't adequate to escape. At a black hole's center lies a singularity, a point where, based on general relativity, space-time bending grows endless. Our current theories collapse here, unable to describe what occurs when reality's structure is extended past its restrictions. Many scientists think a complete theory of quantum gravity will resolve these singularities, exposing new features of how space-time and the universal speed restriction operate at the most basic level. String theory provides one potential glimpse past our current grasp. In this structure, the basic things aren't point-like particles, but minuscule vibrating strings. The varying vibration patterns of these strings form the particles and forces we watch. The universal speed restriction emerges from how these strings interact within space-time's structure. Some versions of string theory propose the existence of extra dimensions past the three spatial dimensions, and one time dimension we feel. These extra dimensions would be compactified, rolled up so firmly that we don't notice them in regular existence. The universal speed restriction would apply within our four-dimensional space-time, but might show differently in the complete higher dimensional reality. This hints at something deep. The universal speed restriction might be a property of our specific slice of a bigger reality. Just as sound's velocity is a property of air, but not a basic restriction on all movement, light's velocity might be a property of our four-dimensional space-time, but not a restriction on movement through extra dimensions. This possibility has inspired ideas like brain cosmology, where our cosmos exists on a four-dimensional brain, short for membrane, floating in a higher dimensional bulk space. Other brains might exist in this bulk, potentially with varying physical principles and varying numbers for light's velocity. If we could somehow travel through the bulk rather than along our brain, we might circumvent the universal speed restriction without breaking physics principles. But there's a vital catch. If such extra dimensions and brains exist, we appear to be firmly stuck on our specific brain. All the forces we understand about, except potentially gravity, are confined to our brain. We cannot merely step off our four-dimensional reality into some higher dimensional shortcut. These concepts stay greatly speculative and face considerable theoretical and experimental challenges. The universal speed restriction additionally plays a vital role in resolving some of the most confusing paradoxes in physics. Consider the celebrated twin paradox mentioned earlier, where the journeying twin ages less than the stay-at-home twin. This isn't genuinely a true paradox, but a counterintuitive result of the universal speed restriction and time dilation. For a genuine paradox, consider a rigid rod traveling at near light velocity. If you suddenly push one end, classical physics would state the other end must travel immediately. Otherwise, the rod wouldn't be rigid. But the universal speed restriction prohibits this immediate influence. The resolution. There are no genuinely rigid things. When you push one end of a rod, a compression wave moves through it at sound's velocity in that material, which can never surpass light's velocity. The universal speed restriction maintains causality and resolves the apparent paradox. Another celebrated thought test is the barn pole paradox. Picture a runner transporting a pole that, when at rest, is longer than a barn. But when running at near light velocity, the pole undergoes length contraction and grows briefer than the barn, at least from the barn's viewpoint. This means there's a moment when the entire pole fits inside the barn, and somebody could theoretically shut both the front and back doors at the same time, trapping the pole entirely within the barn. But from the runner's viewpoint, the barn is what contracts, growing even briefer compared to the pole. So how can the pole fit entirely inside the barn? The resolution involves grasping simultaneity's relativity. Happenings that look at the same time in one reference frame aren't necessarily at the same time in another. The shutting of the front and back doors, which appears at the same time to somebody at the barn, occurs at varying times from the runner's viewpoint. The universal speed restriction guarantees that no genuine paradox happens, merely varying but similarly correct viewpoints. These thought tests highlight a deep truth. The universal speed restriction isn't merely a limit on how quickly matters can travel, it's a basic feature of how causality and information flow through the cosmos. It guarantees that effect invariably follows cause, that tomorrow stays open rather than predetermined, and that the cosmos keeps reasonable consistency. But the consequences reach far past physics into philosophy and even theology. The universal speed restriction possesses deep results for ideas like determinism, free will, and time's character itself. In a cosmos without a universal speed restriction, where effects could spread immediately across any space, the entire universe would be tangled in a web of immediate causation. Your choices now could be affected by happenings occurring at the same time on the opposite side of the cosmos. The separation between earlier, present, and tomorrow would collapse. But our cosmos, with its universal speed restriction, possesses a varying arrangement. Causality flows like a wave, restricted by light's velocity. The cosmos's earlier light cone, all happenings that could have affected the present, is clearly divided from its tomorrow light cone, all happenings that the present can affect. This division forms what philosophers term the now, the instant of becoming where the undetermined tomorrow crystallizes into the fixed earlier. This arrangement might be essential for free will to exist in any meaningful sense. If everything in the cosmos could immediately affect everything else, there would be no local causation, no capability for a system like a human brain to develop based on its own internal reasoning without immediate external determination. The universal speed restriction forms protected areas of space-time where local causation can function before more far effects reach. Some philosophers and theologians observe deep importance in this arrangement. The Jewish philosopher Hans Jonas argued that the universal speed restriction forms the conditions for genuine novelty and freedom to emerge in the cosmos. The scientist and Anglican priest John Polkinghorne proposed that the cosmos's causal arrangement, controlled by light's velocity, permits both divine providence and human freedom to coexist. Whether or not you discover these philosophical and theological viewpoints compelling, they highlight the universal speed restriction's deep consequences for our grasp of reality and our place in it. Light's velocity isn't merely a number in physics formulas. It's a basic feature of the cosmos that molds everything from causality and free will to the quite possibility of life and consciousness. And this takes us back to you, sitting here watching this video. The universal speed restriction isn't merely an abstract idea, it's part of your everyday reality. The light entering your eyes right now permitting you to observe these words, moves at precisely this universal speed restriction. The electrical signals in your brain, enabling you to comprehend these concepts, spread at velocities controlled by the identical basic constant. Your earlier, present, and tomorrow are divided by light cones established by this universal speed restriction. Every cause and effect in your existence, every choice and result, every communication and connection exists within this causal arrangement. You are not divided from these universal principles. You are their expression, a method for the cosmos to grasp its own restrictions and possibilities. The atoms in your body were forged in stars' hearts that burst billions of years earlier. The light from those bursts moved across huge cosmic spaces at precisely light's velocity, neither quicker nor slower. The basic forces that hold your atoms together, that enable chemical connections and biological processes, all spread at this identical universal speed restriction. You exist because the cosmos possesses this specific arrangement with this specific universal speed restriction. If light moved at a varying velocity, stars might not form, atoms might not be stable, and life as we understand it might be impossible. You are not merely in the cosmos, you are of the cosmos, a complex pattern of material and energy molded by the identical basic principles that control everything from quantum particles to cosmic growth. The universal speed restriction reminds us of both our restrictions and our links. We can never journey to far stars as rapidly as we might desire. We can never observe the cosmos as it is now, only as it was when the light departed those far things. We can never flee the basic limits of space and time, but these identical restrictions form the conditions for our existence. The universal speed restriction helps safeguard causality, guarantees materials stability, and permits complex arrangements like stars, planets, and living organisms to exist. What appears like a limit from one viewpoint is genuinely a foundation from another. And there's something deep about existing in a cosmos with this specific arrangement. You can gaze up at the night sky and observe stars as they were years or centuries earlier, their light having moved across huge spaces at the universal speed restriction to arrive at your eyes at this instant. You can transmit a message to somebody on the opposite side of the planet and understand that it will move at the light's velocity, neither quicker nor slower, independent of how you or they are traveling. In a cosmos teeming with randomness and chaos, light's velocity constancy stands as a beacon of order and reliability. It's identical everywhere, for everyone at all times, a universal constant in the truest sense. In a reality where so much relies on viewpoint and reference frame, the universal speed restriction offers a fixed point, a shared reference that all watchers can concur on. This constancy links you to the universe in a deep manner. The identical speed restriction that controls light from far galaxies additionally controls the light reflecting off this screen into your eyes. The identical constant that appears in Einstein's formulas describing spacetime's bending additionally appears in the quantum field theories describing the particles that make up your body. As you proceed about your day after watching this video, I encourage you to occasionally remember the universal speed restriction and its deep consequences. When you observe sunlight streaming through a window, remember that those photons moved for 8 minutes at light velocity to arrive at you. When you utilize your smartphone, remember that the electromagnetic signals it transmits and receives move at the identical universal speed restriction. Remember that this basic constant molds not merely light's behavior, but reality's quite structure itself. It establishes the connection between space and time, between material and energy, between cause and effect. It forms the conditions for atoms, stars, planets, and life to exist. It links you to the universe in manners both delicate and deep. The universal speed restriction isn't merely a reality about the cosmos, It's a window into reality's basic character itself. By grasping why nothing can travel quicker than light, you've glimpsed something essential about the universe and your place within it. You've observed how the cosmos's most basic limits are additionally the foundations that make your existence feasible. So the next time you gaze up at the stars, remember that the light entering your eyes has moved at precisely 182 miles per second, no quicker, no slower. And in that constancy, in that universal restriction that nothing can surpass, you've found not merely a physics principle, but a deep truth about reality's character itself. The cosmos possesses a speed restriction, and that restriction makes everything, including you, feasible. This isn't merely a scientific reality, it's a universal truth that links you to everything that exists, from the tiniest quantum particle to the biggest galaxy. You are part of a cosmos controlled by this basic constant, a cosmos whose quite arrangement is established by the universal speed restriction that nothing can surpass. Thank you for joining me on this exploration through one of science's most deep findings. Please give a thumbs up and subscribe to the channel, and if you appreciated this video, I am confident you are going to love this other one on the left side of the screen. What if humans aren't the first advanced civilization to call Earth home? In this video, I investigate the scientific possibility that an intelligent species might have developed technology millions of years before we humans even existed. See you there. This might seem limiting, but it also means our galaxy, vast beyond comprehension, is our entire inheritance. The Drake equation must be reconsidered. Instead of asking how many civilizations exist in the universe, we should ask how many exist in our galaxy alone. The answer matters because these are the only civilizations we could ever potentially contact. The trillions of potential civilizations in other galaxies might as well not exist from our perspective. Recent SETI efforts acknowledge this reality. Projects like Breakthrough Listen focus on our galaxy and nearby stars, not because we lack ambition, but because physics makes broader searches pointless. We're listening for neighbors in our cosmic city, knowing that cities on other continents are forever beyond reach. The mediocrity principle, the idea that Earth and humanity aren't special, takes on new meaning. We're typical in that we're trapped in our birth galaxy like every other potential civilization. Our isolation isn't unique, it's the universal condition. Every conscious species that has ever existed, or will exist, faces the same impossible barriers we've discussed. The universe's ultimate fate reinforces this isolation. Whether through heat death in 10 Google years, the Big Rip in 22 billion years, or another ending, the cosmos will eventually become inhospitable to life everywhere. Our temporary moment of consciousness in the Milky Way isn't just isolated in space but in time, a brief flicker of awareness in an otherwise unconscious cosmos. After confronting all these impossible barriers, the mind-breaking distances, the laws of physics, the biological constraints, the cosmic expansion that pulls everything apart, you might feel despair. We're trapped, isolated, confined to a single galaxy in an ocean of unreachable islands. But here's the profound truth that changes everything. Our prison is a paradise. Our isolation is what makes us precious. And our constraints give our existence meaning. Being forever bound to the Milky Way isn't a limitation. It's our cosmic inheritance. And it's more than enough. Consider what we actually have. The Milky Way contains 400 billion stars. If we visited one star system every second, it would take over 12,000 years to see them all. At a more realistic pace of exploring one system per year, it would take 400 billion years, 30 times the current age of the universe. Our galaxy isn't a prison, It's an empire vaster than we could ever fully explore. Recent exoplanet discoveries reveal the true richness of our galactic inheritance. The Kepler mission and TESS have shown that planets are the rule, not the exception. Statistical analysis suggests our galaxy hosts over 100 billion potentially habitable worlds. Each one is a complete world with its own geography, weather, possibly biology, unique puzzles that could occupy humanity for millennia. The diversity within our galaxy surpasses anything science fiction imagined. We found hot Jupiters orbiting their stars in days, super-Earths with surfaces of diamond or water, rogue planets drifting between stars, planets orbiting binary stars like Tatooine. The TRAPPIST-1 system alone has 7 Earth-sized worlds. The variety within our single galaxy exceeds what most fiction places in entire universes. Being confined to the Milky Way grounds us in reality rather than fantasy. Instead of dreaming impossible dreams of intergalactic empire, we can focus on achievable goals. Interstellar travel within our galaxy, while extremely difficult, isn't impossible. Generation ships, suspended animation, or life extension could make journeys to nearby stars feasible. We can realistically dream of humanity spreading across our galaxy over millions of years. Our isolation makes us cosmically precious. If life is rare and intelligence rarer still, then Earth might harbour the only conscious observers in the Milky Way. We're not just one civilization among countless others. We might be the only witnesses to our galaxy's beauty. Every sunset, every scientific discovery, every moment of wonder might be unique in our cosmic neighbourhood. This uniqueness brings responsibility. We're not just living for ourselves, but as representatives of what's possible in our galaxy. If we destroy ourselves through war, environmental collapse, or accident, we might be extinguishing the only consciousness the Milky Way has ever produced. Our survival becomes a cosmic imperative, not just a selfish desire. The finite scope of our galaxy makes complete understanding possible. Unlike the infinite universe, our galaxy is comprehensible. Future humanity could realistically catalogue every star, map every planet, understand every phenomenon within the Milky Way. We could achieve complete knowledge of our cosmic home, something impossible if we could spread across infinite galaxies. Being trapped together might save us from ourselves. If we could escape to other galaxies, humanity might fragment irreversibly. But confined to one galaxy, we're forced to eventually reconcile, cooperate, and unite. Our shared imprisonment might be what finally brings humanity together as one species with one destiny. The Milky Way's collision with Andromeda in 4.5 billion years isn't a catastrophe, but an opportunity. Our local group will merge into one giant galaxy, doubling our real estate. While individual solar systems will rarely collide, the merger will trigger new star formation, creating fresh worlds for our descendants. Our prison will expand, giving future humanity even more to explore. Understanding our limits liberates us from impossible expectations. We're not failing to build an intergalactic civilization. We're succeeding at what's actually possible. Every probe we send to another star, every world we terraform, every colony we establish is a victory against the vast distances and harsh physics that constrain us. Our cosmic isolation makes every discovery within our galaxy more precious. When we find life on Europa or Enceladus, decode signals from another civilization, or discover new physics, these won't be routine events in a galaxy-spanning empire, but unique moments in our isolated pocket of consciousness. Scarcity creates value, and our isolation makes every discovery priceless. The artistic and cultural implications are profound. Confined to one galaxy, human culture won't fragment into mutually incomprehensible traditions. we'll maintain enough connection to share art, literature, music, and ideas. The works we create won't be lost to impossible distances, but can enrich all of humanity across our galaxy. Science benefits from our confinement. Instead of spreading our efforts across impossible distances, we can focus on deeply understanding our local universe. The James Webb Space Telescope, the upcoming extremely large telescopes, and future observatories can thoroughly study our galaxy and local group. Concentrated effort yields deeper understanding than scattered exploration. Our limitation teaches humility and wisdom. The universe has shown us our place, not as potential gods ruling countless galaxies, but as conscious matter confined to one galactic island. This humility might be what we need to survive and thrive. Hubris leads to downfall. Accepting our limits leads to wisdom. The search for meaning becomes clearer when we accept our boundaries. Instead of seeking purpose in impossible expansion, we find it in perfecting our corner of the universe. We can transform the Milky Way into a garden of consciousness, a beacon of life and intelligence in an otherwise empty cosmos. Future technologies we develop won't be wasted on impossible intergalactic dreams, but focused on achievable goals. Fusion power, antimatter production, life extension, terraforming, artificial intelligence, all can be directed toward making our galaxy a true home for humanity and whatever intelligences we create or encounter. The story of humanity becomes more coherent when bounded. Instead of fragmenting across impossible distances, our narrative remains unified. Future historians will tell the story of one species in one galaxy, a complete tale with beginning, middle, and end. Our cosmic story has scope and limits, making it meaningful rather than infinite and therefore meaningless. As you look up at the night sky, don't see a prison of unreachable lights. See your inheritance, 400 billion stars that belong to you and your descendants. Every point of light in the Milky Way is a destination you or your children's children might someday reach. That's not limitation. That's abundance beyond imagination. We will never leave the Milky Way, but that's not a tragedy. It's a gift. It means we're home. It means we belong here. It means this galaxy, vast and beautiful beyond comprehension, is ours to explore, understand, and cherish. We're not trapped. We're embraced by spiral arms of stars that define the boundaries of our cosmic kingdom. The universe has given us exactly what we need. Not infinite space that would dilute our existence into meaninglessness, but a bounded realm vast enough for endless discovery, yet small enough to remain coherent. The Milky Way is our cradle and our destiny, our prison and our paradise, our limitation and our liberation. So embrace our galactic confinement. Celebrate that we have 400 billion stars to explore rather than mourning the trillions we'll never reach. Find joy in the fact that we're all in this together. One species in one galaxy sharing one cosmic destiny. The universe has given us the Milky Way, and that's more than enough for any species to find meaning, purpose, and endless wonder. We will never leave the Milky Way, and perhaps in the end, that's exactly as it should be.